In this video, we're going to discuss the Rayleigh-Ritz method applied to an Euler-Bernoulli beam. We're going to apply it to an example of a cantilever beam with a varying cross-sectional area. The beam has a length L of 8 meters, constant width of 0.25 meters. Its height varies. H is equal to 0.5 meters at x1 equals 0 and equal to 0.25 meters at x1 equal 8. It's aligned with the coordinate axis x1. It's fixed on the left end and has a shearing load acting downward of 10 kilonewton on the right end. We would like to find the displacement, the bending moment, and the shearing force on the beam first by directly solving the differential equation of equilibrium, so to find the exact solution, and then using an approximate method, the Rayleigh-Ritz method, assuming polynomials of the degrees 0, 1, 2, 3, 4, 5, 6, and 7. We're going to, of course, assume the beam is linear elastic with Young's modulus E as 20 gigapascal. We're going to assume it's an Euler-Bernoulli beam, and we're going to compare the Rayleigh-Ritz method with the exact solution. In order to find the exact solution, we need to solve the differential equation of equilibrium. This particular example is a little bit complicated because the cross-sectional area is variable. The equilibrium equation that was presented when we talked about the Euler-Bernoulli beam did not take into consideration any beams when the moment of inertia I is variable. When the moment of inertia I is variable, the equation of equilibrium becomes d ei, the second derivative of y with respect to x1 squared, dx1 squared equal to q. So we need to find y that would satisfy this differential equation. A complication arises because the moment of inertia I is actually a function of x, because I is equal to b t cubed over 12, where t is the thickness, or in this example it's the height. So t is equal to 0.5 minus 0.25 x1 over L. And so this is the I as a function of x1. And so you can see when I is input into this equation, you will get a really complicated differential equation that's not easily solvable by hand. We still need 4 boundary conditions, and the 4 boundary conditions are: this end is fixed, and so the displacement is 0 and the rotation is 0. This end is free. The shear force is equal to the applied load, 10,000 Newton, and the applied moment is equal to 0. When we input this differential equation in Mathematica, we seek a solution. The solution looks as shown here. It's a really complicated equation. It's not a simple equation to obtain by hand, and so you can see why an approximate solution would be needed. The equation here, the function y, is a logarithmic function, and it's also a fraction, so it's really not an easy function to find. The moment and the shear, on the other hand, are simple, simply because it's a statically determinate beam. We're going to put the exact solution on the side here, and then apply the Rayleigh-Ritz method. The Rayleigh-Ritz method seeks to find a function y that would minimize the potential energy of the system. The potential energy of the system for an Euler-Bernoulli beam is the integral of ei over 2, the second derivative of y with respect to x1 squared, all squared, minus the forces multiplied by the corresponding displacements. In this example, we only have a force P. The reactions are not going to appear in the equation because the displacement y will satisfy that the displacements are 0 at the supports, and so we're only going to have a force P multiplied by the displacement at x1 equal L. First, we try polynomials of the 0 and 1st degrees. So for both, in order to satisfy the essential boundary conditions, or the boundary conditions of equilibrium for an Euler-Bernoulli beam, we need to find A0 and A1 that would satisfy that the displacement here is 0 and the rotation here is 0. And you can see that to satisfy both, you'll have to get that A0 and A1 both are 0. These are the two boundary conditions at x1 equals 0, y equals 0, and at x1 equals 0, the rotation equals 0. And so the approximate solution would have to be equal to 0, which will automatically be rejected. Next, we will seek an approximation of the second degree. So y is equal to a2 x1 squared plus a1 x1 plus a0. We will remove some of these unknown coefficients by satisfying the essential boundary conditions. At x1 equals 0, the displacement is 0. And at x1 equals 0, the rotation, which is the rate dy by dx1, is also equal to 0. Both would give us that a0 and a1 are equal to 0. And so, the displacement would be equal to a2 x1 squared. The rotation, which is dy by dx1, will be equal to 2a2 x1. The moment is equal to ei, the second derivative of y, with respect to x1 squared. So, will be equal to ei multiplied by 2a2. And when we substitute for I, we get this equation. And the shear is equal to dm by dx1, which is equal to this equation when we take the derivative of this equation with respect to x1. So now we're going to substitute in the equation for the potential energy of the system. Ei over 2 multiplied by the second derivative of y with respect to x1 squared, all squared, so 2a2 all squared, plus the force P multiplied by the displacement at the free end. The displacement at the free end is equal to a2 multiplied by L squared. And so when we substitute for I and for all the remaining variables except a2, we end up with this equation for the potential energy of the system. And so to find the value of a2 that would minimize the potential energy, we take the derivative of the potential energy with respect to a2 and equate it to 0, and we get the value that a2 is equal to this number, from which we get the approximate solution. Y is equal to this number. The moment is equal to ei multiplied by the second derivative of y, so we end up with this equation for the moment, and the shear, we end up with this equation for the shear. And you can see that this approximate solution is really far from the exact solution. So let's see what they look like if we plot them together. You can see that this quadratic displacement is actually not so bad when I compare it with the exact solution. So the displacements are actually very close to each other, the exact versus a quadratic displacement. The moment, the exact moment is a linear function. The approximate moment is not a linear function. It's a nonlinear function, but it's close enough. The exact shear is actually really far from the approximation v2. And so you could see that the third derivative of y is very far from the exact solution. So we're going to try a better approximation. As a better approximation, we're going to try a polynomial of the third degree. And similar to the previous procedure, we're going to first satisfy the essential boundary conditions. And these are, for this particular example, the displacement and the rotation at the fixed end, which will both lead me to the a0 is 0 and a1 is 0. And so the displacement function is y is equal to a3 x1 cubed plus a2 x1 squared. And this is the associated rotation. Moment is equal to ei, the second derivative of y. So this is the associated moment. And after substituting for I, we end up with this equation. and the shear is equal to dm by dx1, so we end up with this equation for the shear. In order to find the unknown coefficients A3 and A2, we need to write the potential energy of the system and find A3 and A2 that would make the potential energy of the system minimum. The potential energy of the system is EI over 2, the second derivative of y with respect to x1 squared, all squared, minus the work done by the external forces, negative p is positive p, multiplied by the displacement of the free end. This is the displacement of the free end. To minimize the potential energy, we take the derivative of the potential energy with respect to A2, we end up with this equation, and then the derivative of the potential energy with respect to A3, we end up with this equation. We equate both to 0, find the value for A2 and the value for A3. This would give us this equation for y. The moment is equal to EI, the second derivative of y, so I end up with this equation. The shear is equal to the first derivative of m with respect to x1, so I end up with this equation. Let's see how they differ from the exact solution when we plot them. In terms of the displacement, the exact solution is very close to the approximate solution using a cubic polynomial. The moment is not so bad, but the shear is still really far. So let's try a better approximation. A polynomial of the fourth order. Satisfying the essential boundary condition, I get rid of A0 and A1. I get a displacement, y is equal to a polynomial of the fourth order after getting rid of A0 and A1. This is the associated moment and the associated shear. The potential energy of the system, EI over 2, multiplied by the second derivative of y with respect to x1 squared, all squared, so I end up with this equation, plus p multiplied by the displacement of the free end. The displacement of the free end is y when x1 is equal to L. Taking the derivative of the potential energy with respect to the three variables, A2, A3, and A4, equating the three equations to 0, we can get a number for A2, for A3, and for A4. And so, a polynomial of the fourth order gives me the shown solution. This is the solution, approximate solution for y, the approximate solution for the moment, and the approximate solution for the shear. The exact solution and the displacement, approximate displacement with the fourth order polynomial are almost identical. The moment and the exact and the approximate are also almost identical. The shear is still further away. If you continue the procedure and use a seventh order polynomial, you'll get a displacement identical to the exact, a moment identical to the exact, and a shear also identical to the exact. So you can see that by increasing the polynomial, your approximation gets closer and closer to the exact solution. I'm now going to show you how to solve this problem using Mathematica. First, the variables b, l, and the height or the thickness as a function of x1, the moment of inertia, Young's modulus, and p are defined. Then the differential equation is solved. So this is the differential equation, the second derivative of y with respect to x1 multiplied by EI, the second derivative of all those is equal to 0. The displacement at the left end is 0, rotation at the left end is 0, the moment at the right end is 0, and then the shear, which is the first derivative of the moment, this all gives me the first derivative of the moment, is equal to p. This is just to make the solution simple. This is an option in Mathematica 10.3. We're putting some assumptions that x1 is only between 0 and L. Then we are able to solve and get the differential, get the solution to that differential equation, and then we can full simplify it and find the rotation, the moment, and the shear. And we can plot them all versus x1 to see the distribution of all. For the second order polynomial, y2 is equal to a2 x1 squared. The second derivative of y, we're going to call it d2y. The potential energy of the system is the integral of ei over 2 multiplied by the second derivative of y squared, integrated from 0 to L, minus the force multiplied by the displacement when x1 is equal to L. Then we solve the equation that says partial with the potential energy with respect to A2 equals 0, and we find A2, and we store that solution in the variable sol, and then we use it as a replacement to redefine the displacement y2. The moment is equal to ei, the second derivative of y2, and the shear is equal to dm by dx1. And then we can plot them to see the difference between y, the exact solution, and y2, which is the second order polynomial. And notice that my choice for y2 already considers the essential boundary conditions. I will also show you the third order polynomial. y3, we're going to call it the third order polynomial approximate solution, we'll call it y3. y3 is equal to a3 x1 squared, a2 x1 squared plus a3 x1 cubed. Second derivative of y is this. The potential energy of the system is the integral ei over 2 multiplied by the second derivative of y minus the work done by the external forces, which is the force multiplied by the displacement at the free end. To find A2 and A3, we minimize the potential energy, so we take the derivative of the potential energy with respect to A2, and then take it with respect to A3, equate both to 0, and find A2 and A3. The equations are between two curly brackets, and the unknowns are between two curly brackets. After we find the solution, we store it in the variable sol, and then update y3 according to that solution. And then the moment and the shear are then calculated based on y3. Then y and y3, m versus m3, and v versus v3 are plotted. And you can copy and paste the code. The code is in your online notes all the way up to 6th order polynomial.